Okay, second go at this one. The first one, all the audio didn't record. Lesson 6 is based on investigating Newton's second law, which, if you remember in lesson number 4, lesson 5, by the way, was just practicing. If we look at the second law, it's investigating this in equation F, the force, is equal to mass times the acceleration. Choose a bigger one. There we go. F equals ma, old classic. So how are we going to do it? Well, I nicknamed it trolley dash. And how we do it is we take a trolley and we put it on the table and we apply different amounts of forces to it and we measure the acceleration. So we want to change the F and we want to measure A. And so that means we're going to have to keep M the same. So the mass of the trolley, usually to slow it down, we just add a little bit of weight on the top, just to keep it from not flying off too fast. So that's the practical in a nutshell. It's really basic. Now, the problem is changing the force on a trolley. Now, you could give it a push. Problem is it's very unreliable. The amount of force you would apply on this trolley each time is very variable. Lots of human error. So instead we use a little trick that we used in year 9. Year 8, we did a nice little practical where we took a piece of string, we attached it to a frictionless pulley wheel, and then we hung off the edge weights, like so. We call them slotted masses. So each slotted mass is 1 Newton. So we have a Newton of slotted mass at the end. We can now apply the force. So that's the force part done. We're going to go from 1 Newton up to, say, 5 Newtons. The other bit is measuring acceleration. And again, a little bit of a problem. We can't use a machine that will directly measure it. So what we're going to do is we're going to measure the distance along the table, distance D. And for example, it's usually around 70 centimetres, so 0.7 metres. And we're going to time it with a stopwatch, how long it takes to do that. So we're going to find the time. And what we can do is we can use this acceleration equation. Now, the bit that we're missing though is this bit, velocity. How do we find that? Well, to do that, we can use velocity is equal to the displacement divided by the time. So if we use that equation, we can take that number, the velocity, and we can put it into this equation. Now we know what the initial velocity is. It's 0. So that's easy. So we're just dividing the distance by the time, and then we're dividing that answer by time again, and that will give us the acceleration. Now, one of the reasons we have required practicals is all the way through. It's not so much can you remember each practical, but do you know what these terms mean at the side? You can see the arrows and stuff from when I first taught it, and then it wiped itself out. So what we're going to be doing is talking about these in terms of this practical. So the first thing is accurate. How are we going to make this experiment accurate? Now, what accurate means is how close to the true value can we get? So how close to the true value. So when doing that, what we're trying to do is we're trying to measure things as best we can. So if we take a bullseye, for example, and this represents all the results, and I could throw a dart, I could have a go at an experiment, and I could get a result. Now the true value is the bullseye. That's the bit you really want to hit. An accurate result would be slap bang in the middle. So in trying to get the true value here, we're going to repeat it 3 times, and we're going to measure very precisely these distances for the distance and the time, and hopefully that will allow us to get to the true value. So that's the first bit, accuracy, how close to the true value. Precision, bit of a funny one this. If you make something precise, so if you're a car manufacturer, you want every single piece of those 10,000 components that make a car to be extremely precise. Now, what do I mean by that? I mean every single piece has to be exactly the same as every other piece of the same type. So in science, that means if I was to do the experiment, all three of my results should be close to each other. So this is high precision here in blue. Oh, a bit too big. I'll do it in green for good. So this is a precise result here. A low precision result, and I'll just get rid of these ones. My ruler's a bit too big. There we go. If I get rid of these, a low precision result would be something like that. And I'll colour those in red. So precise is how close do you get your three answers. So how close together are your, let's put repeats. And I'm going to hit my target. Let's move that out of the way. Take him too. He feels left out. Are your repeats. So three numbers completely the same. Very accurate. Very precise. Now, resolution. Resolution is a really interesting one. Resolution is how closely you can measure something. So here we're measuring the distance. Here. And we're measuring the time up here. So how closely can we measure those numbers? So let's take a look. Here I've got a picture of a ruler. The definition of resolution is the smallest difference you can measure. So the smallest difference you can measure. If we were to take a ruler, you may see some old rulers that don't have the millimeters on them. So let me just mark one off here. The smallest difference I could measure on this ruler is ones. In this case, 1 centimeters. However, if I had a ruler with higher precision, then I would mark off the millimeters. In this case, then, this would have a resolution of 1 millimeter, or to put it in meters, 0.001 of a meter. So that's the resolution of that ruler. It is the smallest difference you can measure. I can measure a difference of 1.0, 1.1, 1.2. So it's this level of resolution. What about the stopwatch? Well, if you zoom in on a stopwatch, I always draw this too small. You have number for hours, 1 hour. You have minute and minute, minute and minute. You have second and second. But then you have two more numbers. You have tenth of a second and you have 100th of a second. So the resolution of this is 1/100th of a second. So that is resolution of this experiment. Now, we've done accurate, precise, resolution. Let's look at intervals. Intervals are the easiest. What numbers are you going up in? So we're going up 1 Newton to 2 Newton. That means our interval is 1 Newton intervals. And you can apply this to any experiment. So basically you're looking at what do you go up in? Nothing more than that. Now, the next one's errors. There has been a really fantastic news article this week. I've been following it for the last few years. And somebody claimed to have violated Newton's, let me remember which one, Newton's third law of motion. And NASA had tested it and said, yep, looks like you've done it. People were up in arms over it. It seemed absolutely impossible. And it was this idea here. I'll just draw a little sketch to show what it means. The idea was that you could create a reactionless thruster. What do I mean? Normally, for a rocket to take off, you shoot something out the back, like that, usually jet fuel, and the whole thing gets pushed that way. That's how rockets work. However, what a scientist was claiming to have found was by emitting microwaves into a funny shaped cavity, this shape here, that you get thrust this way and you do not get any reaction force, a reactionless thruster. Okay, you don't need to go into the specifics of it too much, but everybody's tested it and they kept measuring tiny amounts of thrust. Eventually this week, somebody got to the bottom of it, and what had caused it? It was the wires. The wires that powered the microwave ran past it. Wires, when they have electricity go through them, give off magnetic fields. And so what had the scientists been doing? They'd been measuring the magnetic field of the wire, and it was slightly pushing away, and so they assumed that it was creating thrust. Now, why am I telling you this? Well, inherent in all science is error. It's a quantifiable, countable thing. And we break it down into 3 types of error: zero, systematic, and random. And I'm going to talk about each one in terms of this experiment. So, the first one. We're assuming when this car is on the starting line that it is on 0 meters. Now, if we measure this and we put usually we use a little bit of masking tape on the table. Well, imagine then if, after you've measured it, you constantly have moved the car either too far forward or too far back, but it's always the same. So 0 now isn't 0. That's called a zeroing error. So it's when you have not set, so a 0 error, when not starting at 0. Now, you know you've got one of those when you look at your results and they look a bit like this. So here's my axis. I'm going to use red for bad. And you look across at your friends, and your friends have all got these lovely straight line graphs like yours. However, yours does not go through the origin. And you start thinking, crikey, what's gone wrong? Well, what's happened is you've added on a bit of error. And so what you do is you subtract the error. Do you see that? So if I go to blue, we'll go for green for good. Here's what you should have got. So by subtracting the error away, all your results now will move down to there. So that's how you subtract a 0 in error. You find the amount that you're wrong by and then you add it. The next error is very similar, and it's called systematic. There's another famous example in science about 7 years ago. Somebody claimed to have discovered a particle that moves faster than the speed of light, which is absolutely impossible from everything we know. Made it into the news, the 6 o'clock news. Brian Cox was being interviewed about it. It was big news at the time. It turns out that they had a loose wire in one of the many thousands of connections in their circuit. And as soon after 2 years, somebody investigated it. They pushed the wire in a bit harder and the systematic error went. So what do we mean by a systematic error? It means a little bit added on or subtracted to each of your results through something you didn't control. A really good example of that is LDRs, light dependent resistors. If you remember those, it's like that. And you're doing an investigation, you got your light bulb, but somebody over here has opened a window and you didn't notice that you systematically are adding on light that wasn't there. So somebody shuts the curtains, you've removed the systematic error. However, by the time you've finished, you've already got your results. So if I go back to this graph, again, the extra light will add on or subtract some extra results. So you've got to figure out how much it is and subtract it to get it to go back through the origin again. So that's systematic. The third and final one is random error. Never more so is this when you're trying to play a game of skill, like darts, like snooker, where no matter how hard you try, you can never repeat the same shot twice. Darts in particular is amazing for random error. And that's because no matter how hard you try, nature is so complex. There are so many other variables around that create this effect of random error. Now, how we get rid of that is we repeat the experiment 3 times. Repeat times 3 and find the mean. And that hopefully, if you're still trying to be accurate to get to the close to the true value, will mean that you eliminate or at least reduce the amount of random error. So in this experiment, to now bring this all together, we will measure very accurately with high resolution the distance travelled and the time taken. We will repeat it 3 times and look at how precise our results are. Are they all close together, like the green, or are they all spread apart? Are they low precision? We know the resolution of our equipment, millimetres for the ruler, hundredths of a second for the time. And we know the intervals are going from 1 Newton intervals all the way up to 5. We now know that we are going to make sure we're exactly on the 0 line, and we're going to check for no systematic errors. One here might be that the table isn't completely flat. Maybe it's one side's higher than the other. And we're going to do it 3 times and take the mean. Obviously, we all know what the mean means. And the last thing we're going to look at is the uncertainty. Now, I put the mean in here because that's part of the uncertainty. So what do I mean by the uncertainty? If I go back to this result here, this is what you should get. As you increase the force, the acceleration goes up. It gets quicker. However, you've measured this, and each of your results is a mixture of 3 results. And then you've added them together, divided by 3. Now, how confident are you that that result is exactly where it should be? Well, here's some results I've got. So let's take the first one. Precision, very precise. 42, 41, 43, very close together, very precise. I've done them 3 times, taken the mean to find reduce the random error. Now, how do I find the uncertainty? Well, first of all, I take the big takes small. So in this case, my pen's a bit small here. In this case, I would do 143, 1.43, take away 1.41. And that will give me a range of results of 0.02. So that's range. To find the uncertainty of those results, I then take the range and I divide it by 2. So I do 0.02 divided by 2 gives me an answer of, now I'm going to I'll show you why in a minute, plus minus 0.01. That is the uncertainty of that result. Now, plus minus. If I look back at this, say it was this result in the middle, I'll put a bit of orange on it. It's this result. I know that the result went up. If this was an average of 1.42 there, I know that actually it could be as high as 1.43 and as low as 1.41. So when I write plus minus 0.01, this is why 0.01. It's showing you I can be up, above or below by that number. Let's take the next one. Precision. Good or bad? I'm hoping you're all saying bad. It's terrible. They are not precise at all. There's massive differences. So let's find the range of this. 2.28 minus 0.28 equals 2. There's the range. Let's find the uncertainty. 2 divided by 2 equals plus minus 1. What does that mean? It means if we were to go back here and use the same idea, this time my range bar is massive because I am plus or minus 1 above my average of 1.28. I can be as low here as 0.28 and I can be as high here as 2.28. So in science, if you ever see a scientist say, there is error, we always think of error as being bad. Well, in science, you quantify it. You can never eliminate it because the more you try to eliminate it, the more there is some creeping in. So we accept there is error, and this is that practical. Now I've attached this as well. The one that it explains here is for posh kids that have got a posh school with loads of posh stuff. They talk about using a light gate, and you'll see this in the textbook as well. We don't have them, but they're quite nice little things to have if you have one. You can use it like a stopwatch, so you can press go, and it'll break this little bit of card here. This bit will break it first. This bit will break it second. There's a laser that goes in between them. A little bit of light. Let me just rub that out and put red in for laser. Like that. And it can actually measure the instantaneous velocity, because it starts the stopwatch there and it ends the stopwatch there. So it can actually find the time it takes to go from there to there. So over a very short distance and time, it can tell you the instantaneous velocity at the light gate. So that's one way to do it. I don't have that, so I just literally get you guys to time it. The other way, and it's really quite tricky, I hate doing it, I've tried it once, I will never do it again, is to find the velocity at the beginning. So if I find the time, say here and here, so you have 1, 2, 3, 4, 5 people with stopwatches. Let's call them time 1, time 2, time 3, time 4, and time 5. Well, what you can do is between 1 and 2 there, you can find the distance and the time it takes to go between them, and you can find the velocity. Let's call it V1. And you could do it for here to here, d over t. So you could actually plot the change in velocity as it moves along. You could have 1 result, 2 results, 3, 4, and if you're feeling really clever, 5. You could have T6 when it hits the thing. And you can have the velocities along as it goes. And between each one, you could find the acceleration. It's a nightmare, so we won't be doing that ever. The one I do is enough. So this is the sheet that goes with it. I think that's about it. I've got some questions for you to have a go at. Use it in conjunction with the PDF, and hopefully the audio's worked on it this time. Any questions, just email me. If you feel that you're too far behind not to catch up anymore, just do a little bit. Hit the done button, hand in, and I'll mark it as done. All right, take care. Bye-bye.